Welcome to the video on electrons and atoms in the periodic table, Chapter 9 of our chemistry series. In this video, we will explore electromagnetic radiation, the Bohr and quantum mechanical models, electron configurations, and various periodic trends. We will examine how scientific models explain the properties of elements, such as the reactivity of group 1 metals and the inertness of noble gases, based on the periodic law. These models, specifically the Bohr and quantum mechanical models, provide a framework for understanding how electron behavior dictates the physical and chemical characteristics of elements. Scientific pioneers like Niels Bohr and Erwin Schrödinger significantly advanced our understanding of quantum mechanics, though they found the concept of wave-particle duality quite profound. The study of how light interacts with atoms was essential in developing our current models. Light is electromagnetic radiation that travels at a constant speed and displays both wave and particle properties. This diagram illustrates the relationship between energy, wavelength, and the emission of light as electrons transition between different orbits within an atom. Think of light waves like ripples on a water surface. When the water is disturbed, waves radiate energy outward from the point of impact. Wavelength, denoted by the Greek letter lambda, measures the distance between two adjacent wave crests. White light contains a spectrum of colors. Red light has the longest wavelength, while violet light has the shortest wavelength within the visible spectrum. When white light passes through a prism, it separates into its constituent colors, often remembered by the acronym Roig-Bev. Objects have color because they reflect certain wavelengths of light while absorbing others. For example, Ard's shirt appears red because it reflects red light. Frequency, represented by the Greek letter nu, is the number of wave cycles passing a point per second. Frequency and wavelength are inversely related. Light can also be viewed as photons, which are individual packets of energy. Shorter wavelengths carry more energy per photon than longer wavelengths. In summary, electromagnetic radiation acts as both a wave and a particle, with energy levels directly dependent on wavelength and frequency. Let's explore the electromagnetic spectrum in more detail. This spectrum includes all types of radiation, from high-energy gamma rays to low-energy radio waves. As you can see on this chart, visible light is just a small portion in the middle, while high-frequency radiation is on the right and low-frequency is on the left. Gamma rays are at the end of the spectrum, representing the shortest wavelength and most energetic photons. They are produced by stars and certain unstable nuclei. X-rays follow gamma rays. While useful for medical imaging due to their ability to pass through many substances, they carry enough energy to damage biological molecules. Next is ultraviolet or UV light. It is more energetic than visible light, and excessive exposure can lead to skin damage, cataracts, or increased cancer risk. Visible light ranges from violet to red. While these photons don't damage biological molecules, they interact with our eyes to allow for human vision. Infrared light has even longer wavelengths than visible light. It is emitted by warm objects, which is why it is used in night vision technology. This infrared image demonstrates how heat is captured. Warmer areas appear as red, while cooler areas are shown in dark blue. Moving further, we find microwaves. These have longer wavelengths and are used for radar and cooking, as they efficiently heat substances containing water. Finally, radio waves have the longest wavelengths. They are essential for modern communication, including radio, television, and cellular networks. When comparing different types of radiation, remember that wavelength, frequency, and energy are all linked. You can test your knowledge by ordering them. Ionizing radiation, like X-rays, has a unique medical application. Doctors use this high energy to target and destroy molecules within cancer cells. During radiation therapy, while the goal is to kill tumors, healthy cells may also be affected, which is why precise targeting is so critical. Beyond general radiation, atoms exhibit unique behavior. For instance, neon gas glows red when energized, creating the distinct light in neon signs. Different elements produce different emission spectra. As shown here, mercury vapor appears blue, while hydrogen gas emits a characteristic pink light. Unlike the continuous spectrum of white light, the emission spectra of individual elements are composed of specific, distinct wavelengths, almost like a chemical fingerprint. Hydrogen is a perfect example of this. When energized, it emits light at very precise wavelengths that are unique to its structure. To explain these unique results, Niels Bohr proposed a model where electrons orbit the nucleus at fixed distances. The Bohr model established that electrons exist in specific orbits, each corresponding to a set energy level. Crucially, energy in this model is quantized. Electrons move in fixed orbits, like rungs on a ladder, and cannot exist in the space between them. When a hydrogen atom absorbs energy, an electron is excited to a higher orbit. When it returns to a lower energy orbit, it releases a photon of light. Because the energy difference between these orbits is fixed, the light emitted has a specific, corresponding wavelength. Each line in the spectrum represents one of these transitions. This chart maps specific transitions, such as the electron dropping from the fourth orbit to the second, or the third to the second, matching the observed spectral lines. While the Bohr model successfully predicted hydrogen spectrum, it failed for elements with more than one electron, leading to the development of the more advanced quantum mechanical model. The transition from the Bohr model to the modern view marked a shift in how we perceive the internal structure of atoms. In this new quantum mechanical model, the defined orbits of Bohr are replaced by orbitals. These are not paths, but maps showing the probability of finding an electron. Electrons do not travel in predictable paths. Instead, an orbital represents the statistical likelihood of an electron being in a certain region when probed. Consider the difference between a baseball, whose path is easily tracked, and an electron, whose movement is fundamentally probabilistic. While you cannot track the exact trajectory of an electron, observing many events reveals a pattern, which we represent as a probability map. In modern chemistry, these probability maps provide the foundation for understanding atomic behavior, moving us beyond simple planetary models.